Okay. So now we come to Fourier analysis on the circle group. This is where Fourier analysis really started actually. So the circle group is it is the unit circle in the complex plane e to the I theta 0 less than equal to theta less than 2 pi. Okay, so this is the with under multiplication. So the identity is 1. So this is also isomorphic, of course, to the 0 to 2 pi under the equivalence 0 to 0 is equivalent to 2 pi. So meaning you take the segment and do the quotienting where you identify 0 and 2 pi. Okay, so which is addition modulo 2 pi. Okay, or you can work with the real line with addition modulo 2 pi. Which means actually it is R mod 2 pi z. So that is one way to write it. If you, it's another way to say it. I mean, so you look at the real line. So here we are looking at the, in the second picture, we are looking at the line segment where these 2 points are identified. Here we are looking at the infinite line, the real line, and we identify any 2 points which differ by 2 pi. So this is the equivalence class. If x is here and x plus 2 pi, they are identified. They are the same point. So that's the quotienting that is going on here when we say R mod 2 pi z. Okay, so you can use any of these notations and so on, but it doesn't matter much. So you can do all of them. So I will probably stick to this. I can't promise that. Yeah. So what is it that we want to do? So so this is a group. It's a group under multiplication. Abelian group under multiplication. Okay. But unlike with the finite situation, here there is a bit more. So what are characters? So let's come to the question of characters. So here, this also has a topology, right? This has a topology. If you are not familiar with abstract topology, just think of the metric. I mean, so there is a sense of what is close, what is far. So there is a distance function on this thing. But there's something about this topology. It's not, it is a topology in under which group operations are continuous. Of course, we take it for granted. That's obvious. What do I mean by group operations are continuous? So if you're sending x, y to x times y from t cos t to t. This is a continuous function, right? And sending what is the other operation? Taking inverse. This is another map from t to t. These are continuous. So these operations are continuous. So the topology is not something independent of the group multiplication. The group multiplication is compatible with the topology in the sense that it is continuous. So that's what it is saying. Okay, so okay. The reason I mentioned it is later I will remark on the general situation, which of Fourier analysis on locally compact abelian groups, but yeah, but we'll come to that. We'll stick to the circle group for now. So what do we mean by characters? Why do we say that? Okay. Character means it's just like before, it's a homomorphism from our group. In this case, it happens to be our group. Okay, so that's what here. But the range is always the circle group, right? So we always took that to be circle group. So, but we had an additional condition that we want it to be also continuous. We are in a situation where topology matters actually. So we want not any homomorphism from our group into T, but continuous homomorphism from our group into the circle group. Okay, so this target was always the same. Even when we were looking at finite abelian groups, the target was the circle group, and that will stay. Since I'm going to stick to abelian groups, it will stay. So this is the definition of characters. So what are the characters for? What are the characters? That's the question. So example. So if I define chi n of e to the I theta to be e to the I n theta. I could perhaps have written just z goes to z to the n. It's the same. So I have to remind myself, I write e to the I theta instead of z. So z goes to z to the n. So this is a map from, it takes an element of our group and gives another element of this, and it is a homomorphism. For any is a character. For any integer, it can also be a negative integer. Okay. Chi 0 is the trivial character. Note that chi 0 just sends it to 1. So chi 0 is just, this is the trivial character. But there are so many of these characters, and it was an exercise I had given, and I will just repeat that here. Okay, so exercise is that these are all the characters. Show that these are all the characters of the circle group. Okay, so there is no other. This is a kind of familiar type of problem. Fx plus y is fx plus fy, then show f is linear. You need a little bit of condition on f. That's why I made it continuous. Okay, so we assume continuity. So you get the regularity needed to conclude that these are all the ones that you get. Okay, I will leave that as exercise. So we get, like with the finite, what was it that we did in the finite abelian group case? We considered all the characters and they formed a basis, okay, for L2 of G. In the finite group case, when for finite abelian group, so we saw that G hat provides an orthonormal basis for L2 of G. How was that? How was that? So we checked the orthogonality. We check that two different characters, that is two different elements of G hat were orthogonal. And then we just also saw that G hat cardinality is the same as the cardinality of G. Hence, by dimension considerations, G hat forms an orthonormal basis. It was orthogonality was already checked, and the dimension considerations did it. Now, what orthogonality do we have here? Okay, so that is something that I mentioned in the very first class. This is the single most basic point in all of Fourier analysis. that this is true. So because, so maybe I write here, so so it is the most basic point. So let's write here. So if you look at, but now maybe I write here. So in case of on T, what happens? So if you look at any two characters, chi n and chi m, now we have to take inner product in L2 of T. Okay. So here I'll have to say a little bit. I mean, so I want to check. I earlier had asked this question, but this didn't come till now. This is, I mean, I assume everyone is familiar with it. I may not be able to spend time on explaining this too much, but I can give some reading material, or one can carry on without, but I'll ask. So this is the space of L2. So this is the space of Lebesgue integrable functions which are square integrable. Actually, sorry, Lebesgue measurable functions that are square integrable. So the meaning of this is just instead of sum, we will have the integral. What is the meaning of L2 of T? What I mean is always chi n of e to the I theta, chi m bar of e to the I theta, d theta over 2 pi. I always take the measure to be d theta over 2 pi. Okay, so this is something that you can notice that. So this will be L2 of T will always have this normalized Lebesgue measure. When I was working with finite abelian groups, I did not normalize the measure. I just took the counting measure. Here I have normalized it to 1. There is no fixed convention, so people do different things. So the 2 pi will show up somewhere else if you don't normalize here. Somewhere else it will fly. So you cannot avoid it entirely, but we'll just do this. Okay, so this part is actually, so what is this actually? So this one is just the integral from 0 to 2 pi e to the I into, this is e to the I n theta, this is e to the I m theta conjugate. So this becomes e to the I n minus m theta d theta over 2 pi, which we know is 1 if that number is 0, the exponent there. If that is 0, then you have integrating the function 1 with respect to this normalized measure, so you'll get 1. Otherwise, you get 0. Okay, so that is the orthonormality. So in other words, the orthonormality is still okay. In L2 of T. Okay, so at this point, maybe I ask, so are there people who are completely unfamiliar with the basics of Hilbert space and orthonormality projections, this type of things? I had earlier asked people to tell me, maybe 1 or 2 people responded. Response was, I think that we have seen it, but maybe good to recall, but I'm not sure now. So I'm asking again. So is it okay? Everyone understands L2 space and Hilbert space. Is that okay? A good reference for this, I mean, so there are many references. You can take up any number of books. Concise one is Rudin's real and complex analysis, has a chapter on LP spaces and then Hilbert spaces. So yeah, I will talk about measure and so on, but by and large, no great subtleties will come. So the point is the Lebesgue integral is absolutely essential to have completeness of these spaces. If you use the inner product of this kind of inner product on Riemann integrable functions, you don't get a complete space, and the whole point of Lebesgue integration is to complete these spaces. That's the gist of it. By and large, you can follow it. If you are not too familiar with it, you can still follow it. But if anyone wishes me to explain or give some references, etc., I will be happy to do that. Okay, you can tell me after. Are there any comments here? No.
My knowledge is very basic, but yeah, maybe
Yeah,
I'm an exception. Yeah, and I'm not crediting. So thanks.
No, but how basic? Like, I mean, you are familiar. Have you seen measure theory once? Or?
Yeah, I've seen a little bit. Yes.
Oh, you have taken a measure theory course once.
I have done some stuff online. Yes.
Okay, okay. Then probably you are okay with. I mean, you have seen LP spaces. Then you know what is Lebesgue integral, and you know what is LP space,
Yeah.
perhaps.
Yeah, the distinction, the Riemann integral and Lebesgue integral, like I am sort of lost on that distinction
Okay.
in integrability and how that changes things. I didn't quite get that.
Lebesgue integral just is a more general integral. By doing the integration procedure, limiting procedure in a different way, Lebesgue manages to integrate more functions. That's all. So you can think of Lebesgue integral as a direct generalization of Riemann integral. More functions are Lebesgue integrable than Riemann integrable. What it primarily does, that is the fundamental point of it, is that this type of spaces become complete. That was the whole purpose of Lebesgue integration, that you complete these spaces. If not, you could think of more and more general integrals, but that's not the case. Once you define Lebesgue integration, all these spaces become complete, and complete in the sense of metric completion. Cauchy sequences converge, and that is the gist of it. Okay?
I see. LP spaces become complete under Lebesgue integrals.
Yes, that's
Okay,
the
thank you.
most important point
Got
of it, actually.
Okay, thank you. That's
How
okay.
to define it, how it was done, the mechanisms will not be so important. All you need to know is that they complete, and then there is some basic general theory of Hilbert spaces, that Hilbert spaces have, if they are at least Hilbert spaces have an orthonormal basis, which is really a countable set if this space is separable. In all our situations it is. So that is another, so that is what, there is a chapter on Hilbert spaces in Rudin, but any number of other books also on basics of orthonormal basis and projections. Hilbert spaces are very much like finite dimensional inner product spaces. I mean, it's comes as close as possible. So that's the
Okay,
yeah.
thank you.
Okay. So let me go ahead, but if there are troubles, you can always interrupt me. I mean, maybe I can add some explanation which makes it locally understandable then, but maybe one can read a bit on the side. I can discuss with you further if needed. Okay. Yeah. So let's take this. So the question is it an orthonormal basis? Okay. So orthonormal basis, let's remember what the question is. Question remains. Okay, so that is saying that is this orthonormal set actually a basis. So let's just very quickly recall some very basic points that, so if you have H, a separable Hilbert space, so what that means is it has an inner product. There is an inner product which induces a norm. This is norm square, under which the norm allows you to measure distance, under which H is complete. Okay. So one of the basic facts of Hilbert spaces is that so when I say separable, it means this in this metric, this has a countable dense set, which is true for all things like L2 space and so on. You can take polynomials. I mean, you can take, yeah, you can get many polynomials. I mean, sorry. We will in fact show that it's separable, but there are many countable dense sets you can pick. Okay, that's not a big deal. But fact is that then H has H will have such a Hilbert space will have an orthonormal basis. There exists by no means unique orthonormal basis. Let's say Vn. So here I'm indexing by, since I don't have any particular reason, I'm indexing them by 1, 2, 3, and so on. Meaning, the reason I just recap this is to mean what is the meaning of orthonormal basis. First of all, they form an orthonormal set. And zero otherwise. This is one, but it should also allow you to write every function in terms of this, but that's no longer a finite linear combination, unlike in finite dimensional vector spaces. For any u in H, we can write u as sum over n equals 1 to infinity. The coefficients will be u inner product, so Vn is my basis. U inner product with Vn, that will be this. So the meaning of this infinite series in vector spaces in linear algebra, you can only add finitely many, but since here we have a metric, we can add infinitely many. And the meaning of this is that the meaning is nothing but taking partial sums. If you take up to capital N, this series, these are scalars and this is a vector. So this is another element of the Hilbert space. If you take the norm squared, that goes to 0 as n goes to infinity. So this is the meaning of okay. So it may also be worth recalling that it just means, so when does that, so another small point that I will recall, I mean, it's all, it's not a, yeah, so if when Vn, recall, if Vn is an orthonormal set, then, so these are equivalent statements. Vn is an orthonormal basis is the same as saying that if you take the span of these things, V1, V2, etc. Span is all finite linear combinations of these, and then take the closure in the Hilbert space. That gives you the whole of H. Okay, and that's also equivalent, a very useful criterion. This is the most useful way in which we always do that, is that there does not exist any non-zero vector that is such that is orthogonal to all the Vns. So this is these are different ways in which we say, I mean, so orthonormal basis means that you can expand any vector in that, but it is useful to remember that it just means that the closed span of these Vns is the whole of H, and that there's nothing orthogonal to all the Vns. Okay, so if some vector is orthogonal to all the Vns, then it must be the zero vector. So coming back, that is the sort of question we are asking here. We have found an orthonormal set in L2 of T, namely the characters. These are all the characters. Okay. Question is it an orthonormal basis? So just to be very clear, here I gave an exercise to show these are now all the characters. If there was one more character that would have been orthogonal to this, maybe. Okay, I haven't argued in that sort of abstraction, but you can believe that if there was one more character, they would be orthogonal. and there doesn't. That is what this exercise says. But to show completeness, it's not that. That's not the point. There should be nothing in L2 which is orthogonal to all these characters. Okay, so is that true? That's not clear. There is no other character, but is there no other? Is there nothing in L2 which is orthogonal to all these chions? In other words, is this enough? So this is the primary question that we want to address now. Okay, is there any question about this? What we are asking? So, by the way, just to say quickly, this is not. I mean, this is a natural question considering what we have done in finite groups, but it goes back to the very beginning motivation that I gave from vibrating string problem. Okay, so where is it? In the introduction, I talked about the vibrating string problem, which was, yeah, this kind of stuff, right? So you remember, just very quickly, let's go over that. So in the vibrating string problem, we had this, and we, by separation of variables, we found some particular solutions, like this cos pi nt sin pi nx and sin pi nt sin pi nx. So what it is, yeah. So here the question was, so these are particular solutions, cos pi nt sin pi nx, sin pi nt sin pi nx. So the point is, by taking superpositions of these kinds of solutions, for example, if I take summation an sin pi nx, that, I mean, sorry, an cos pi nt sin pi nx, this is a linear combination. That is also a solution to the same equation because it is linear equation. Okay, it's a linear equation. So any superposition of solutions, this and this, are actually solutions. You can even take some linear combination of these two things. What that allows you is that your initial conditions are more general. If you just took one of these, the initial condition would be a sine curve or a cosine curve or something. But by taking superpositions, we can get more general initial conditions. So a natural question was, can every initial condition, can it be thought of as a series like this? Not with finite n, that is clear that you cannot do that, but maybe with infinite n. That is, if I take an infinite series, in my solving the differential equation, I don't start with solutions. I start with initial conditions that I want. Question is, that function f of x, which I want as the initial condition, can it be written as a superposition of sine functions? If so, then I have also found the solution as a superposition of those particular solutions. Of course, in all this, what is the notion of convergence? Various issues are there. But you see that that question is not a purely academic question. It is coming back to the original motivation of this. What functions can be written as superpositions of sine functions? In the very beginning, this was quite a bit of surprise to people, apparently, that how can you write a non-periodic function in terms of sine functions? Yeah, it can be done. I mean, so various things are possible. So that is the, going back to the question. So here we are using only sines, but more generally here we are using sines and cosines. That's what the complex exponentials are. Okay, so that's what this question comes back to, whether every function in L2 of t can be expanded in terms of the characters. Okay, so that's what this is. So that's what we are asking. Can every function be expanded in terms of characters? So we can use any of these criteria. If you want to show that the answer is yes, you have to show either that yes, every function can be approximated by these functions in L2. That's what it means. Span closure is H, means that finite linear combinations of these VIs can be used to approximate any vector in H. So in other words, here you would have to take some function and show that it can be approximated in L2 of t by finite superpositions of characters. Or you try to show that if some vector is orthogonal to all the characters, then it must be 0. So you have these options open to you. But the problem is not entirely trivial, and in its time, it was a major question which was settled by, in a very famous theorem, by Fourier. Even before that, people did Fourier analysis without the full rigor, but Fourier solved the problem. Okay, so So that is Fourier's theorem. But before coming to that, so how can we approach this question? How to show it? So answer is yes, actually, by the way. There is no mystery here. Yes, but not obvious. The point is all these type of ideas that were in finite dimensional situation of using dimension consideration is out of the window. Yeah, we have infinitely many characters and L2 of t has infinite dimension, but that doesn't mean anything. You can throw away half the characters also, it will still be infinite set. So that doesn't say anything. So dimension considerations are useless. So it's not obvious, unlike in the finite group setting. So how to approach this question? So how to approach this question? So the point to show what we want to show, given f in L2 of t, there exists some superpositions. So let's call it some fn, gn, let's say, of the form which are some finite gn, which is a finite superposition of chi's. Okay, so let me just not write a formula. Gn is a of these characters such that it approaches f in L2. Okay, so this is what we want to show. But as in analysis always happens, you don't have to take the problem. If you just stay with it, you will never make progress. You don't have to work with general L2 functions and so on. It would be fine if you also can show in, okay, so rather let's just take this, let's for a moment, yeah, okay, sorry. So this is actually, okay, sorry, let's do this. So more or less, this is actually equivalent to, let me put it this way. So the most, this is more or less equivalent to, but here what matters is that this is implied by. So what would be the best approximation for f, right? So we saw that in a general Hilbert space, this is what we will take. We will take this. So a natural thing to try. So natural thing to try would be to take finite linear combinations of characters with Gn equal to, let's take k equals minus n to plus n. Since my characters are indexed by integers, the most natural thing would be to take okay, this would be the most natural approximation to take, right? This would be the best one based on chi minus n to chi n. So with Gn equal to chi minus n, show that so if you could show this, then you have found, of course, what I care most is about the reverse implication, that if you can show this, then you get this. But more or less that is equivalent. If you don't want, just to be clear, let me erase this side. This is more or less the same. But what I care is like this. It seems the most natural candidate to take for GL, right? So you take you take only the characters from minus n to n and take the obvious linear combination of this kind, which you do in an orthonormal expansion. This is really what it is this is really projection of f onto the span of chi k with minus n less than equal to k less than equal to n. It is the 2n plus 1 dimensional space to which you are projecting. This is the projected vector, projected function, vector, whatever you want to call it. So it is the projection, and that seems the most natural one. So in other words, projection means it's the closest element to f in this span. So it seems the most natural one to show. How would you show this? How would you show that this is true? Okay, that is the difficulty. I mean, so we don't know how to show this. So one of the things we do in analysis is that if it would be enough to do it for nice enough functions. It would be implied, but this is, I'm going to write a false fact. Okay, so this is not true, that with Gn as above, show that Gn minus f sup norm goes to 0 whenever f is a continuous function on the circle group. Okay, suppose we manage to show we don't directly work with all L2 functions, but work with only continuous functions. Okay, so look at continuous functions on the circle group and try to show that Gn is even better approximated, maybe in sup norm. If you could show this. This implies that. Why does this imply that? Because the L2 norm is bounded by sup norm, right? So why is this? So first one is that Gn minus f 2 norm squared is 0 to 2 pi Gn minus f squared d theta over 2 pi, right? Now, if you have shown that the sup norm is small, that is bounded by Gn minus f sup norm squared and integral of 1, which is 1 because of d theta over 2 pi. So this is bounded by this. So if this goes to 0, then this also goes to 0. But this we are showing only for continuous functions. But second point is C of t is dense in L2 of t. So I am assuming this fact also, that continuous functions can be used to approximate L2 functions in L2 norm, not in uniform norm. That can be done, of course. So for example, indicator function of an interval, you can't approximate in uniform norm by continuous functions, but you can approximate by L2 functions. So what I mean is, if you have, here I'm talking of circle group, but think of just, I mean, I'll write it in the segment. Suppose I have a function which is like this, indicator of an interval and 0 outside. There is no way you can approximate it in uniform norm by a continuous function, but if you take the natural approximations like this, which is 0 up to here and goes up and stays there and then comes down in a very tiny interval. If you make this interval small, the L2 norm bit of the difference will also be small, because yes, there is a difference between the two functions on this short interval, but that difference is bounded by 1. And the interval is vanishingly small. So you do get that. So like that, in fact, it's a basic theorem that L2 functions can be approximated by continuous functions. When you take these two facts together, you do get it. The only problem with this is that this is false.
Sir?
Yes.
What do you mean by uniform norm, the infinity norm?
Oh, sup norm, Gn of.
Yes.
So when f is continuous, this also will be continuous, by the way. Everything is continuous. So this means the sup norm is it is in this case the maximum, in fact. Of theta minus f of theta. Okay, I was writing e to the I theta, but okay, so same thing. It's what I mean. So when f is continuous, Gn is also continuous, by the way. It's easy. These are some numbers and chi k are continuous functions. Actually, Gn is always continuous. Sorry. irrespective of what f is, Gn is always a continuous function. It's a superposition of characters which are continuous functions, finite superposition. So this is Gn is continuous, f is continuous, supnorm is the maximum difference between the two. Okay. So, but this turns out to be false. This is not true. And so how to approach is not clear. So this is where Fourier came up with his brilliant idea. So this is now, afterwards you have seen this, but this was probably the first time somebody thought of this type of an idea. So what Fourier did, is the following. So for f in C of t, define Gn as above. F in a product chi k with chi k. That is not going to, okay, I should probably at some place provide an example for this, that it doesn't work. I will look up, okay, I cannot do that. When I say it is false, there are counter examples. There are continuous functions for which it is not true. Now I'll have to look up to give you the example, but this is true. But anyway, so Gn doesn't work. Take it on faith now. Gn doesn't work. Now what Fourier did was to define Hn, which is an average. Okay, for I equals 0 to n. So this is defined for n greater than equal to 0. So G naught G1. So you take the average of the first n. So you know, generally you may have seen theorems in basic analysis that if a sequence of numbers converge to, say, xn's converge to x, then if you take the averages, that is x1 plus up to xn by n, that average also converges to x. Okay, so because so usually averaging makes if convergence was happening, averages also converge. Converse is not true. I mean, in real numbers, we know that, for example, if you take sequence like 1 minus 1, 1 minus 1. Okay, sorry, this is bad example, right? No, this is an okay example. So here, this does not converge. But averages. So let's say this is the sequence x. If you take yn is x1 plus up to xn by n, then that is, what is it? It is 0 if n is even and 1 by n if n odd. So this does go to 0. So averaging only improves convergence. Okay. So this is a general point. But here is a case where you have averages to converge, but the original sequence doesn't converge. So this, what Fourier realized was that GNs are not good, but if you average them, they are good. So then Hn converges to F uniformly on T, which is same as saying subnorm of Hn minus F goes to 0. This is what we mean. Okay, as a corollary, so what? I mean, so, but I did not have to take this Gn. This Gn was my own harebrained idea, possibly. We said that we had to find finite superpositions of characters which approximate F. Now, Hns are also finite superpositions of characters. As a corollary, immediate corollary is that form an orthonormal basis for L2 of T. Okay, so that is the consequence, because Hns are also, reason is that Hn belong to span of the, when I write span, it always means finite linear combinations. So Hn belongs to this, and for f in C of t, Hn minus f 2 norm is bounded by Hn minus f infinity norm, which goes to 0. And so for f in C of t, it works. So if f is in L2 of t, find f tilde, which is in C of t, such that f minus f tilde L2 norm is less than epsilon, which we can do because C of t is dense in L2 of t. So I'm writing down the argument now, and then find Hn, if you want, put a tilde such that f tilde minus Hn tilde. Hn tilde, now this is a continuous function, so it's approximates like this. You can find such a thing. Hence, with these two, we will get that f minus Hn tilde 2 is less than 2 epsilon. So for every L2 function, you are able to find a trigonometric polynomial. That's what finite superpositions of characters, since these are power functions. Okay, these are e to the I n theta, powers of e to the I theta. Linear combinations of them are like polynomials, but we call them trigonometric polynomials. So for every L2 function, we find a trigonometric polynomial which is arbitrarily close in L2 norm, which shows that there is a sequence of them which converges to f. So this proves the corollary. Okay, so that's how the corollary follows. I wrote it in more detail than possibly needed, but anyway. So the key point is this idea of Fourier, that we can do this, that if you take a further averaging of the natural approximates, then that works. Now, if you are willing to ignore history and jump ahead, actually there is a simple way you can deduce this fact that we are trying to get to. Okay, but what is that fact? So we are trying to say that trigonometric polynomials. So so here is an alternate way. Check that if you take finite superpositions of characters, what can we say about this? This is a vector space, right? This is all finite linear combinations. So this is a vector space, but you can also multiply things. Why can you multiply two things? Because product of two characters is again a character, right? I mean, chi n into chi m is chi n plus m. So product of characters is characters. So this is actually not just a vector space, it's an algebra. So meaning you can multiply. So satisfies the conditions of Stone-Weierstrass theorem. Okay, so if you don't know what is Stone-Weierstrass theorem, ignore this comment. But if you know Stone-Weierstrass theorem, you can immediately check that. So Stone-Weierstrass theorem tells you that if you have a vector space of continuous functions on some compact metric space, let's say, which satisfies some conditions. So it has to be a closed under multiplication and it has to separate points. So if you can check all that for this and conclude that this span is dense in C of t, of course, with the sup norm. Hence, dense in L2 of t with the L2 norm. Okay, so if we are willing to ignore history, then the fact that what I wanted to say here, I could have said it, there exist finite superpositions which approximate in L2 is something that you can get by Stone-Weierstrass theorem by showing that finite superpositions are dense in the space of continuous functions, it's sup norm. That's what Stone-Weierstrass gives you. And then because C of t is dense in L2 of t, you can get this second statement. But in a way, this is not entirely satisfactory, unless you, well, if you know Stone-Weierstrass theorem well, it's okay. But even if so, most likely the proofs you have seen of Stone-Weierstrass actually use either Weierstrass theorem or Fourier's theorem. Okay, so there are proofs which don't use that, I think, but I don't. Okay, the ones I recall do use Weierstrass theorem or Fourier's theorem. So in a way, it's better to prove this statement. Also, it's a bit more explicit, though I don't know whether that is of any use directly. But it is a great idea. It's a fantastic idea, and it is nice. The proof is also very nice. So we'll try to see why this works. Okay. Any questions, comments so far? So I gave this alternate way. You can take this as exercise. But I am going to prove Fourier's theorem directly. We will prove that if you take GNs as this natural approximates, they are actually best approximates in L2 sense. But you have to take further averaging to get uniform convergence even when f is in C of t. Okay, any questions, comments? Okay, if not, let's see what is Gn and Fn are. Okay, so now let's come to the proof of this. Let's come to the proof. So towards the proof, so I probably won't finish the proof. Okay, so let's look at first. So let f be in C of t. Okay, so we have defined Gn. You remember Gn is defined as so Gn. Okay, sometimes I write e to the I theta, sometimes I write theta. Okay, so I hope that is not a big confusion. F inner product chi n, chi k, k equals minus n to plus n, and then multiplied by chi k of theta, right? So what is this? This is actually, if you see, this is the same as this inner product is 0 to 2 pi, which I write as just t. Let's use a different variable than theta because I have fixed theta. So let's use phi maybe. F of phi, chi k of phi conjugate d phi over 2 pi. That's the integral. The sum goes, it's a finite sum, plus minus n to n. Then I have chi k of theta. What is this? I mean, let's interchange the integral and sum. It's a finite sum, so there is absolutely no problem. This is the integral over t of f of phi against what? You take the sum. The sum, f doesn't depend on k, so it comes out. And what I have is a sum over k equals minus n to plus n. Chi k of theta, chi k of phi bar d phi. So that's what I have. So let's look at what that function looks like. So this one, what is this function actually? So you see that so it's f integrated against some function of theta and phi. That's what we have written. So we will analyze what that function is. K is minus n to plus n. This one, which is same as, since these are homomorphisms, it is chi k of theta minus phi. Okay, theta minus phi, I mean e to the I theta into e to the minus I phi. So that's what that is.
That 1 by 2 pi is still there, right, sir?
Ah, yeah, you're right. You're right. So that 2 pi is outside here. So let's leave the 2 pi here. So I have this function, 2 pi is still there. So chi k of theta minus phi, but this is what? This is, we know what this is. So it is k equals minus n to plus n e to the ik into theta minus phi. Okay. So let's just call it dn of theta minus phi. Okay. So that this becomes f of phi dn of theta minus phi d phi over 2 pi, the integral over the circle. Okay, so that's what this whole thing becomes. And we can write an explicit form for dn. So now I'll just write dn of alpha, because dn of theta minus phi, it's a function of the difference. Applied, it looked like the function of two variables. It's actually a function of one variable applied to the difference of the two variables. So dn of alpha is actually, this series is a geometric series. So if I pull out e to the minus in alpha, what I see is that it is 1 plus e to the I alpha plus up to e to the I into 2n alpha, which is a geometric series. It is e to the minus in alpha into e to the I.
It's 1 o'clock.
Okay, I will end with this e to the I n plus 1 alpha minus 1 e to the I alpha minus 1. Which if you just you pull out sorry, this is 2n plus 1. 2n plus 1. So let's pull out n of this. E to the in alpha I pull out here. So which is actually, that cancels, sorry, I pull out e to the I n plus half alpha. So I'll just write it as e to the I. So I have pulled out n plus half. So remaining is n plus half. But here I have pulled out n plus half. So it is e to the minus I into n plus half alpha. So I pulled out e to the I n plus half alpha. E to the I n alpha cancels. E to the I alpha by 2 is still remaining. I'll take that out by making e to the I alpha by 2 minus e to the minus I alpha by 2. Okay, I pulled out an e to the I alpha by 2 here, e to the I n plus half alpha here. So you get this. Now it's a difference of two things, exponential minus its conjugate. So it is 2i times sine of that. So it is actually sine of So what it looks like is like this. Okay, we will discuss more next time. So Gn looks like this. What does Hn look like? We will talk about that and complete the proof next time. Okay, I'll stop here. Any